Thank you very much. And what you're trying to do in your classrooms is really, really important to the faith of our children and to the good things that will happen in their life if they learn and learn to reason and to think and to ponder, not just about the science of things, but also about the ethics of things and about how God works in our universe. So today, my goal is to models of light and the experiment that birthed quantum physics. Chris called me on the phone and he said, Tim, what would be the most important physics lab of modern physics that they're presently doing? What would it be? And without hesitation, I said the photoelectric effect. It birthed how we understand modern physics. It has a lot of things about it that are very interesting and counterintuitive, and it would be a really good experiment. And so Chris went after it, and he made it happen. And I'm really glad to be able to share this with you. I actually used the photoelectric effect in my classes at the end of the year. In every single lab we did, and we did about 22 labs in a year and tried to figure them out together. Every single lab I chose, I thought, will this help explain the photoelectric effect? And so everything led to the photoelectric effect. So it took 8 months to get there, but it was really worth it. But it won't be hard. We're going to just do it in 2 hours. And you all are very capable students. You're going to do 8 months in that 2 hours. And in fact, we're going to cover 2,600 years of physics. That's advanced. To review how we came to understand light scientifically over the last 2,600 years. To help our participants come to a greater comprehension of the experiment that birthed quantum physics, the photoelectric effect. I have a video that I want to show. And I just want to ask you, this is a young adult who's explaining what they think will happen if they're put into an absolutely dark room. And I just think it's a very good little clip on teaching science. And it's not just teaching science, but I think on teaching. It's a very good clip. So here we go.
Karen and Richard are students in middle school. Like many children and adults, they believe, incorrectly, that our eyes can see, even in a room that is totally dark.
This is a room with like lead walls, 3 feet thick. And it's like down a mine shaft. You know, it's like there's no way light can get into it. There are no windows and doors. Somehow we made this room around you. We're going to let you out. There's plenty of air. You're okay in there. Doing this experiment. Okay, absolutely dark.
Okay.
Can you see after 5 or 6 minutes? Can you still see the apple?
You can see it, but it wouldn't be red. It wouldn't have a color. It would just be gray or like a lighter shade of black than the rest of the table.
No light gets into this room in any possible way. What do you see?
I'd still be able to see the apple just because it's like lighter than the rest of the room because it's a different color than black. It would be red and I'd be able to see it better.
Karen and Richard believe that in a totally dark room, objects lose their color but remain visible in shape. Although in darkness, the eye adjusts so it can detect even the faintest amount of light. In a room with no light whatsoever, there is nothing for our eyes to detect, and we cannot see.
I suppose one reason people don't think you need light in order to see is that we're rarely ever in a situation when we don't have light around. I mean, we can always see, can't we, essentially? There's always some light there. We don't know what it's like to be in a totally dark environment.
The room Karen and Richard are in has been specially prepared so that when the lights are shut off, it will be absolutely dark.
Have you ever been in a completely dark room?
Yeah.
Well, tell me about that.
Well, it's just like it's completely dark, and then in a little while, like if you're with other people, then it's completely dark, and then in a little while you can like start to see their shape, but you can't see them. You can just see their like shape.
Yeah. Where were you in a completely dark room?
Well, it's been like a couple times, like whenever there's a power outage, or if you turn off the light before you go to bed, when like all the windows are closed or whatever, shades are down.
Have you ever been in a completely dark room?
Mhm.
Where was that? Tell me about it.
Sometimes when I was younger, we used to play flashlight tag, and you'd have to turn all the lights off in the house and go down, hide somewhere. So I'd go down in the basement and just hide down there. And I wouldn't be able to see anything, but after a while I'd be able to make out what I was looking at.
I think very few people have actually been in a very dark room. I know that when I go into a photographic darkroom and it is really dark, it's a totally different experience from being in my bedroom at night when it's dark. Because there's always some light, some very low level, but there's something there.
Well, would it be possible for you or for somebody to make a room that you couldn't see in?
No, I don't think so. Because your pupils can always adjust. So you can see a little better than like when you first, because your pupils get bigger. So like if I were to go completely black now, then we wouldn't be able to see very well, but in like 5 minutes we'd be able to see a little better. But we wouldn't be able to see perfectly. You know what I'm saying?
I think I do.
Now let's shut the lights and prove to Karen once and for all that without light she cannot see.
Okay, here we go. 1, 2, 3.
I can't see anything right now. It's completely dark.
Okay. Can you see the apple?
No, not yet.
Are you sure you're looking where the apple is?
I have no idea.
Can you hold your hand up in front of your face and see if you can see that?
No, not yet.
Now, how long do you think we've been in the dark so far?
Minute.
So how much longer before you can start seeing things?
I think about like 4 or 5 more minutes. Something like that.
Why is it impossible to make a room where you can't see anything?
Well, because no matter what, your eyes will always be able to adjust. Like moles live under the earth and they can see, but they can't see in the light.
You said before something about how you know this stuff. Can you tell me how you know what you're telling me?
Well, about the light and stuff, it's just like when you're in a dark room, it's like obvious for you to know that in a few minutes you'll be able to see better than you were when lights first went out. Like that's given from experience. And plus we've done experiments in school, like watching, like you have a partner and you watch them like bring their eyes out from the dark and watch other people shrink and stuff. And you just know because of stuff you put together in your head. And I've never even thought about these questions before, but my answers make sense to me.
Well, you seem to have a lot of ideas. It's been about 6 minutes, somebody just told me.
Oh, okay. Well, I guess I was wrong then.
Well, no, really. Do you think you were wrong, or do we have to wait longer?
Well, it's okay. You can turn back on the lights. But I think eventually your eyes will adjust. Like, it might take a couple years, but they will.
We. Now what do you see?
Everything.
Did it make you think anything different from what you thought before?
Well, I guess it takes longer than a few minutes, but I do still think that your eyes do adjust.
So her solution was to say, first she said, oh, your eyes will adjust in about 3 minutes. Then she changed to, it will take 5 minutes. When she was confronted and saw for herself, she then said, it will take a couple years. Right? Why do you think that is? Why do you think people will cling to something when they actually see that it's not true? Yeah.
Pride.
What's that?
Pride.
Pride? Maybe. Yeah, it's possible that, I mean, don't want to be wrong. So now what I'd like you to do is you're in teams, right? Theoretically, you're close to each other. I would like your teams right now, and I would like for the second person listed in that team to be the one who stands up and tells us what you come to. But I would like you're going to generate, you're going to try and make an explanation to somebody who has been blind all of their life. They've never seen anything. They've been blind since birth. And I want you to explain to them what seeing is. Okay? And so I'd like you to get in a group and come up with some sort of explanation for what seeing is to someone who's born blind. What I want to point out to you is how important metaphors are in science. Because a lot of times we're studying things that we never really see. We're talking about things that we can only think they exist at the smallest levels, and it's not possible for us to detect them with our senses at all. And the use of metaphors is extremely powerful. You can transmit a lot of information by saying colors are like notes, amplitude is like brightness, volume is like brightness. It ends up that metaphors are the key to learning. And I'm reading a book right now called The Birth of Mathematics, and it's really good because that is the entire assertion, is that metaphors, we were using metaphors even prior to learning how to talk. And they have evidence of that among infants. So that's really an interesting thesis. So what could be the reasons that models fail? Well, they might be the wrong metaphors. And they might tell us things, that these metaphors might tell us things that don't work. How could one describe light and seeing? Okay, go to the next one. Okay, the ancient view of light. In the ancient view of light, can you go another? It was like streamers left from the eyes. And now, let me just say that metaphors in science are not always universally used by every scientist alive at the time. I am fully aware that some scientists in Greece thought differently, and that there was argument and debate. But these were ideas that were written about and that were accepted. And in this case, the ancient Greeks and those who were educated in 170 years before the Common Era, 300 years before the Common Era, they thought that streamers left your eyes, scanned the objects around you, and then returned to your eyes. That's what they thought. In fact, maybe that's what that girl thought, because she thought you could see in a totally dark room. And I want to say that we shouldn't assume that they were believing in magic, because if you take your finger and you press hard enough on your eye, you're going to see lots of different colors and things, and you'll probably feel pain. And when you do that, that could create credence to the fact, oh, your eyes are producing some beam that goes out and then comes back. I often thought in the comic books when I was a kid, there was Superman had X-ray vision, and they would show these streamers coming from his eyes, okay? And it's a misunderstanding of how the eyes work. And it's okay to have a misunderstanding because you've never been given the metaphor. The metaphor for the eye is, it's a detector. It receives information from your environment and interprets it. Your brain then interprets that information. Does light okay, so one of the questions that came up was, does light instantaneously fill space, or does it take time to travel from one place to another? Think about how fast light moves. When you turn on the light, it's like everywhere instantaneously. It like fills the room immediately. And but this idea that light might take time to travel, people began to wonder about it. And the first known person to question the idea of the speed of light was in the 5th century BC philosopher. And what is it? Anybody want to help me with that? Empedocles. Less than a century later, Aristotle would disagree, and the argument continued for more than 2,000 years. And so some thought that light did take time to travel, and some thought, no, it's like some sort of instantaneous ether that just appears everywhere at the same time. The speed of light was cracked by Romer in 1676, and he was like an assistant to Cassini. Io is a moon that goes around Jupiter, and it's almost visible to the naked eye in some dry parts of the country that are at altitude. I know that. But definitely with just weak magnifying glasses, you can see the moon's going around Jupiter. In fact, you'll see like 6 specks going around it. And Io is the biggest one, brightest. And it goes around the moon about every 42 hours. It is eclipsed by Jupiter. So then it goes behind Jupiter, and then it comes back out on the other side a little while later, and then 42 hours later, it just repeats that cycle over and over again. They realized this, and so we have, this is the sun. This here, whoops, go back. Okay, this right here is the orbit of the Earth around the sun. And then this here is Jupiter. It's not drawn to scale. This is Jupiter. Let's say the Earth is right there. Let me talk about the Earth being located at H. Okay? When it's located at H, Jupiter is said to be in opposition. Very common terminology among those who do astronomy. What opposition means is at 12 midnight, you look straight up, and there's Jupiter. If you're on the Jupiter side of the Earth in the nighttime, and it's midnight, and you look straight up, there's Jupiter. That would be when Jupiter's in opposition. It also happens to be when Jupiter's closest to us. It also happens to be when Jupiter's the brightest. It also happens to be a great time to visually engage Jupiter with a telescope. So anytime you know a planet's in opposition and you're kind of excited about that, you take your telescope out and you go to some place and you look at it, because it's the brightest, closest it's going to be to the planet Earth if it's in opposition. About every 42 hours, it would rotate around Jupiter. The eclipse was 10 minutes later when the Earth was located at K and F in its orbit. For example, let's see, that would be, actually, if the Earth was located here, I'll just explain this for a second, and you were at midnight and you looked on the horizon, there would be Jupiter. Okay? This would be K and this would be F. Those would be at points where right in the morning and right in the evening, you would be able to see Jupiter on the horizon. When you were able to see Jupiter on the horizon at a different time of year, it occurred about 10 minutes later. The eclipse was 10 minutes late. Now you might say, oh, that's not long at all. Well, to them it was long. Hey, it's supposed to be eclipsing, but it's not. And it was Romer who cracked that. He suggested that the reason why is because this length from H to Jupiter is shorter than the length from Jupiter to K, or Jupiter to F. And, so I should use my dot right here. So this goes further. That distance right there is further. In fact, the additional distance, if I go to pen and I say pen, the additional distance from G to here, right? And then we say H. I'll say that's about the same distance, right? H. It's going an additional distance. And they would draw it to scale on a piece of paper and then calculate the distance that it went. And so they began to have, this is in 1676, they began to think about their light did have a finite speed. It just didn't fill all of space like some material. All right, let's continue on. The eclipse is 10 minutes later at K and at F compared to Jupiter in opposition at H because the speed of light was constant and the additional distance across the Earth's orbit was significant. I put this in here because I thought it was important for you to understand the event, when it happened. Romaire's colleagues almost universally expressed doubt about his theory. Cassini almost didn't want him to tell people because he thought it wasn't true about Io. Romaire responded by calmly telling them that Io's 9th of November eclipse in 1676 was going to be 10 minutes late. When that time came, these astronomers gathered and they stood flabbergasted as the movement of the entire celestial body lent credence to his conclusion. He predicted the delay in the time. Romaire, now see, we have a model here. He has a model, and he's explaining an observation, and this is providing a change. Now, which model is he using here? He's using, of course, the Copernican explanation for how things rotate about in our heavenly bodies. Romaire's colleagues were right to be astounded at his estimation, and even today his estimation of the speed of light is considered to be amazingly accurate, considering it was made 300 years before the existence of both lasers, the internet, and Conan O'Brien's hair. Okay, so it was 80,000 kilometers per second too slow, but given the state of science and technology at the time, that's remarkably impressive, particularly since he was primarily working off a hunch to begin with. Actually, he had the wrong distance of the Earth to the Sun. He had the wrong distance of the Earth to the Sun and from the Jupiter to the Sun, so therefore, when you corrected for that, he was like within 2% of the correct value for the speed of light in 1676. That's an amazing accomplishment. An amazing accomplishment. Let's continue on. Okay. In 1729, James Bradley used Romaire's explanation for the time delay due to speed, but revised the speed estimate based upon a better data in Jupiter's distance and also Earth's distance. And the estimate was found to be within 2% of the correct value. All right. If light has a speed, could it be a particle? This particle would be like very fast, very small, and perfectly elastic. And that was proposed by Isaac Newton. Continue on. Newton's particle model became very dominant, especially during the time of his life. He was the sort of character that you did not want to not get along with, and he was very prominent in his area. And so I would do a number of experiments with my students to verify that light was a particle. And one of the experiments you can do is it explains triangles and rectilinear propagation, straight line pathways, and particles explain it all. And in fact, we do a whole bunch of shadows. If you change the distance of the object and you carefully measure the height of the object and the height of the shadow and the distances from the source of the light, you can calculate an unknown. You can estimate the size of your shadow. If you're a movie director and you want a shadow of a certain size on the wall, you can have somebody estimate where they have to stand to get the shadow to be the right height on the wall. So you can do this. I'd have my students do it and establish ratios and proportions. So I found it was really good for establishing ratios and proportions. Continue on. There's also pinhole cameras use the idea of where light is traveling in a straight line, rectilinear pathways. It lands on a photosensitive paper, and you hold it still. This is a picture of Matthew Fitzgerald, my great-great-grandfather, who died in the Civil War fighting for the wrong side now that I live in Alabama. He's a great guy. We have a picture of him with a pinhole camera. His daughter married a judge, so she married into money. And they got him a pinhole camera when he came back for vacation from the war, and then he went back. He died in the Battle of Cedar Creek. But my wife has a general in the Confederate Army on her side of the family, so we got a picture of him. They're both together up on the wall. And but he was a true soldier. The general was in charge of medical logistics, so he didn't do nearly as much as he did. All right, continue on. The other thing is that as you get further away, the light is spread out onto a larger area. And so the light gets dimmer as you get further away. So particles, light as a particle explains how the intensity of the light drops as you get further away. And that's also rectilinear propagation. If you're twice as far away, you're going to have 1/4 the amount of light. If you're 3 times as far away, you're going to have 1/9 the amount of light. I used to use the example of spraying butter on toast. If I spray butter on toast that's this distance, right, then I have that amount of butter on that toast. But if I go twice the distance, I can spray 4 pieces of bread at the same time, but I would have only 1/4 the amount of butter. So I would have to turn the butter on for 4 times longer. If I went 3 times the distance, I would have 9 pieces of toast collecting the butter, and I would have to have the butter nozzle on, the butter sputterer I called it, on for 9 times as long. And by the way, the butter sputter is not my idea. It's from an old PSSC physics video that I saw when I was in high school, and that was a long time ago. It was just after Ben Franklin taught me physics. Okay, next one. I've seen a lot of physics develop over my centuries. All right, the other one, they're very small. For example, you can take 2 lights and you can shine them. And you would say, well, if light is a particle, they should bang into each other, right? So I would take 2 basketballs, and one kid would be over here and one kid here, and he throws the basketball, and this one hits the basketball in the middle of the air. And they do a pretty good job. Then I change the basketball into tennis balls. And you got to be careful, because sometimes some people can do that. You know, they can hit a tennis ball about 1 out of every 4 or 5 times. But then you change it to golf balls. And they just love this stuff. They love throwing golf balls and tennis balls flying all over the room. It's just so much fun. Make sure they're wearing helmets and visors and you know, knee pads and all that. Back in the old days, I didn't worry about it, but now you got to do that. 35 years ago. Very small, rare interactions of light beams in regions of space. So they must be like extremely small, because you could eventually throw marbles. So this person would be throwing a marble in the air, and someone way over there is trying to hit a marble. What's the chances of 2 marbles hitting? Pretty slim. Well, that explains why these light particles don't bang into each other. They pass right through each other because they're so extremely small. All right, and this is Isaac Newton doing all this explaining. Then how about reflected rays? Well, if I take that ball and I throw it against the wall, it bounces off at exactly the same angle. If I take a basketball and I bounce it off the floor really fast, you got to get somebody who can bounce a basketball really fast, and you always have someone in the class who can do that. And it comes off at the same angle from the normal. So from here to here. All right, next one. And this reflection, this principle can be exploited to make mirrors that will produce images of where objects are not. And so this would be called a real image, because if you look here, real beams of light are coming from there, and it's really cool. There's a whole bunch of experiments that you can do with curved mirrors that will verify that light travels in straight lines, bounces off at angles that are equal on both sides of the normal to a surface, and it's definitely a particle. All right, continue on. And then, how do you explain refraction with particles? Well, some particles, according to Isaac Newton, some particles will bend faster than others, and it like filters them. If they bend faster, then they're going to come out on the low end because they have a steeper angle or a larger angle away from the normal. And those objects that are bigger that are more massive are not going to be changed in speed, and they're going to be closer to the normal. And that was how Isaac Newton explained it. Although the way he explained it was, I'll tell you how he explains it in optics, that gravity of the two objects, they interact for gravity, and that larger objects are, pulled and sped up more slowly than the smaller, less massive objects. All right, continue on. And so it has a tendency to sort the particles out. And so that's basically a summary of the corpuscular theory of light proposed by Newton, which, because of his reputation and his dominance throughout science in Europe, that was pretty much what people accepted. Perfectly elastic, okay. They were very fast, evidenced by rectilinear propagation. That means a straight line. And we also do that with a basketball. If you throw a basketball slow, it arcs. And the faster you throw it, the straighter it is, the less the arc. Very small, rare, no interactions of light crossing the same areas of space. Perfectly elastic. Perfectly elastic. These light particles bounce and are perfectly elastic. All kinetic energy is conserved. The kinetic energy of the particle coming in is the same as the kinetic energy coming off if it's reflected. Speed changes, refraction of light when traveling through objects of different densities, and then colors. Different colors result in differences in the size of the corpuscles. All right. And so I give my students a test, and they answer all their questions about light being a particle correctly, and they make a good grade, and they're really happy. They did good on all the labs. And then I start out the next unit, which is the light as a wave. And here we have Father Grimaldi. Now this is Grimaldi's pizza, but it doesn't have anything to do with Father Grimaldi, who actually studied an important property that decimates light as a particle. It's not possible for light to be a particle. And my students at this point are so mad at me. You just spent 5 weeks proving light was a particle, and now you're doing this experiment. And basically, if you were shooting particles, you would expect a shadow. If I put a hair or a thin little tiny slit, I should get very defined shadow where the light is and where the light is not, and then that's it. But instead, what I get is a pattern on the other side of the object that's not just a shadow. And it's called a diffraction pattern. And it violates light as a particle's behavior. It's not rectilinear pathway anymore. There's something going on at the edges of these objects. Number one, the first to make accurate observations of the diffraction of light was Father Grimaldi. Okay? And he demonstrated and observed the passage of light could not be reconciled with the idea that it moved in a rectilinear path. You would hit an object or go through a slit, and then you would make a beautiful pattern on the other side that could not be explained by light as a particle. Finally, he discovered what are now known as diffraction bands, and we're going to be seeing those directly. Continue on. If you have, let's say, waves, and the waves have two sources. These waves interact. And they form peaks that are twice as high where peaks cross. Peaks that are twice as high where peaks cross. You'll get this pattern, and if you look sideways down a water wave tank, you'll see patterns of peaks going in this direction, peaks going in that direction, peaks going in that direction, and you can analyze water waves using mathematics. And it works. The analysis of diffraction patterns using the pattern made by water waves is exactly the same for light as it is for water waves. It's the same formula. And so you can find that this is the distance between slits, and I would spend a lot of time with my students describing exactly how you could calculate the wavelength, which is down here. That's the wavelength. You can figure out the wavelength. Can we reduce it now? You can figure out that wavelength right there by getting the angle that this red line is going at. And so then you can set up a ratio. I'd say this is the mama triangle, and that's the baby triangle. So L is to this is L. L is to Y as the wavelength is to the distance between the slits. Because this is a mama triangle and that's a baby triangle, and I developed that whole line of thinking using geometry. And that's what Young did. And so this is a diffraction equation where you can predict that along here is going to be a bright spot if it's a wave, and then over here will be a bright spot if it's a wave. And sure enough, they would do the experiment and shine the light through known slits or known widths of hair, and they would calculate the width of those, they would calculate the wavelength. Or if you know the wavelength, you can calculate the width of the hair. And so that's kind of a neat one. Everybody wants to know if they have hair, exactly how wide is it, right? I mean, it's something they're interested in. One idea was that light was a wave. By the way, that's a metaphor, isn't it? I mean, we don't see light waves. We see colors. But we assume if it's a wave, right, some things. And one of the things that came up was the speed of light particles were supposed to be faster and denser substances if it was. Einstein had said that the objects would speed up when they got closer to the substance that it was passing through. For example, that the glass or the diamond would suck in the light and speed it up, and then it would come out on the other side. Well, it ends up that Foucault actually measured the speed of light in water using an apparatus that involved mirrors and bright light sources in 1672. And he was able to find out that it went slower in water than in air. And it was just exactly the opposite of what you would expect. All right. Snell's law explains it completely. If you're in a fast medium, the distance between these two waves is going to be further because it's going a further distance in the same amount of time. If you're in a slower substance, then the distance between these waves has to be closer because it's going slower in the same amount of time. And the rule is that the waves have to be connected at the boundary of the two mediums. So this down here would be a slow, that there would be a fast. And so what happens is that the light comes in, and then boom, it goes toward the, it bends and goes towards the normal. And this supported light as a wave. And so my students would do Snell's law experiments, and they would measure the refraction in glass and light and make sure it's right. Diffraction is fully explained by the wave model. Refraction is fully explained by the wave model. Color's behavior is consistent with wavelength. Waves pass through without altering propagation. In other words, waves pass through each other. Remember we were talking about how light, they shine through each other? Well, waves pass right through each other. If you look in the water, you have waves from here and waves from there, they pass right through each other. They don't interfere with each other. They don't stop each other. Be careful with that word, interfere. Reflection of waves are predictable. So they bounce off surfaces just like balls that are perfectly elastic bounce off hard surfaces, so don't waves do the same thing. Maxwell's calculations exactly predict electromagnetic disturbance and yields a wave propagation. So Maxwell ran the numbers on this, and he said, well, what if an electric wave is causing a magnetic wave in a perpendicular direction? And he measured the response of developing of the interrelationship between the electric field and the magnetic field when it's produced. And what he found was that it was exactly the same as Romère's speed. The speed of light from Jupiter was explained with electromagnetic waves. And it was really surprising to him. And he went to Faraday in person, who was much older by then, and Faraday had speculated it was an electromagnetic wave, and he shared it with them. It was a great accomplishment. Increased energy of the light is provided with increased intensity. If I increase the intensity of light, I have larger amplitudes. of the waves coming in. All right, continue on. Waves require medium. Ether is the medium for light. So the trouble with light as a wave is that waves need something to be in. They have to be in some medium. So water waves on the surface have water. Sound waves are compression waves in the air. When the ground shakes, it sends waves in the ground. Earthquakes will send waves in the ground all around the Earth that can be measured continents away. And the question became, okay, so if light is a wave, what exactly is it going through? And so the search began for ether. Unspoken is that diffraction is a tendency for waves when they interact with a surface to spread, to curve. Okay? That's diffraction. Then there's constructive interference, where you'll have different diffractions occurring in a system, and then the different waves produce patterns of amplitudes. So when we say diffraction, it's actually shorthand for diffraction and constructive interference. And I just want to make that clear that this is a common way we speak, and it's confusing to the students too, as well as to teachers that might be here as well. I just want to point out that we're very well aware that the patterns themselves, although we call them diffraction patterns, are the result of two things: diffraction and constructive interference, where peaks of waves are crossing in the same places in space. You have brighter areas. The challenge, Huygens Wave Model, the challenge was that the waves require a medium. Is ether a medium for light? So now I'll go back to Isaac Newton. Isaac Newton, when he was done writing optics, he talked about the corpuscular theory of light. But then, in the later revisions of optics, he began to say that that light could be treated as if it was passing through an ether. And he examined that, but he was never convinced of it fully. But he realized that argument existed. Michelson and Morley, they wanted to find out if the ether was really there. So if the ether's standing still and the Earth is traveling through the ether, and we're going at a right angle to the ether and we shine a light, we should see the light travel at a different speed. If it's going into the ether, it would travel at a slower speed if there's an ether wind. That is, when the Earth is moving, it produces like a wind, and it would change the direction of the light or the speed of the light or some combination thereof. And so Michelson and Morley worked on that, and they were highly respected. They came up with the speed of light using equipment on large concrete foundations floating on mercury. And they did extremely meticulous work over the years, and were never able to find the speed of light vary by even the smallest amount. They spent years trying to prove that ether was present and that it could be detected in a different speed of light as the Earth traveled through this ether. Einstein proposed studying light speed through ether as part of his Ph.D. But then he found out they had already done that. So, everybody who's gotten a Ph.D. understands that issue. Somebody else has already done that. Oh, well. Okay. But he became interested in, one of the things he became interested in after he did get his Ph.D. was the photoelectric effect. In the photoelectric effect, you can shine a light on a metal, and you can actually produce electric current. You can knock electrons off the metal by just shining a light on it. And it depends on the color of the light, particularly if it's ultraviolet light. That's really, really a high frequency, very short wavelength. And it will produce, in a lot of metals, even in plastics even, it will produce electrons coming off. The process of ejection of the electron from the surface when light falls on that surface is called the photoelectric effect. and it's also known as photoemission. And this was known in the late 1800s. They were aware of this, and a guy named Leonard actually studied this in detail. What was interesting was that if you increase the light intensity, you fail to increase the energy of the electrons ejected, as the wave model would predict. Light at too long a wavelength fails to eject any electrons at all. If it's the low frequency, for whatever reason, they don't know why, if it was a lower frequency or a redder color, it wouldn't knock electrons off the metal. And so the photoelectric effect was very intriguing because it acted in ways that were not understood. And so Einstein ends up writing a paper, a page and a half long, using the data collected by a guy named Philip Leonard, who spent 40 years working on trying to catalog, like, what are the things you can change about the photoelectric effect? Well, you could change the color of the light. You could change the intensity of the light. You could change the metal that the light falls on and measure the current. You could change, then you could find out the energy of the electrons coming off by applying an electric field. So you could use like what's called stopping voltage. 1 volt would stop the electron coming off. You would say, well, then the maximum electron kinetic energy must have been 1 eV, 1 electron volt. And so, next one. So now we're going to do some data collection. I have 2 photoelectric apparatus, but I want to kind of touch back at the beginning of this thing. If you don't have the right metaphors for light, the experiment is kind of hard to figure out because you don't see waves. You don't see particles of light. You just see colors. And it's the metaphors that are driving our predictions and expectations. And if you're confused, that's a really good sign, because that means you're transitioning to a better metaphor, like that girl in the movie. At some point, she's going to transition to a better metaphor after she goes through her physics class. And it's the same for all of us. And think about how hard it is to change your metaphor, right? When you want to cling to something, it's really hard to say, I've got to change. So, number 1, participants are going to gather data concerning the behavior of the photoelectric effect using simulations. So we're going to have groups in here working on simulations, gathering data, and Matt's going to guide you in that. Number 2, there are going to be participants that are going to go in the other room, and we're going to operate the equipment together. I'm going to be there with you, and we're going to collect data exactly how modern physicists collect data. They turn knobs, they get readings, they write them down. And don't turn the knobs too much because smoke might come up and fire alarms might go off. Okay, and then we'll have to delay the talk. 3, participants share data and patterns found and discuss if the explanation proposed by Einstein for light quantum is consistent with findings. So we're going to talk more about that, but right now we want to, about Einstein's expectations for this and what his talk is. So during this grueling talk, 2,600 years of review, physics explains the world using analogies, metaphors, imagination, speculation, logical consistency, and refines the explanations based on both observations and predictions that are both qualitative and quantitative. And that's how science is done, and that's how we think as scientists. Modern physics, quantum mechanics, emerged as a result of coming to see particles we will never really see. We see particles we never really see. These photons interact with the smallest of atomic, subatomic particles, allowing us to probe the universe in ways that extend our ability to observe directly with our senses. Kinetic energy of the ejected electron, E subscript K is what I use to represent that. That was your stopping voltage, the absolute value of your stopping voltage times the number of electrons involved, which we said was 1, and it's electron volts. HF is the size of the packet of light coming in to the metal. And it's Planck's constant times the frequency of that light. And then minus phi, which is the work function of the metal. The work function is how much energy does it take to kick an electron out. Oh, this is a lot better. How much energy does it take to liberate an electron? I like that. It's a much better way of putting it. Einstein proposed that the photoelectric effect is fully explained. This is the metaphors he's using now. Number one, that light is thought of as a discontinuous rather than continuous. Instead of thinking it as a wave that's continuous across space, let's think of it as discontinuous. Number two, an individual quanta of light has an energy consisting of the product of the frequency and Planck's constant. Now, where did he get that from? He got that from Planck himself. Planck had been working on putting energy into metal and observing the frequencies of light that were generated. So he went the opposite way. And so Einstein recognized that, and he said, okay, that's HF. And number three, all the energy in the quanta is delivered to a single electron. So all the energy in a single quanta, and that was his word for photon. A photon, as far as I can tell, I'm not sure about this, but it appears really after Compton's experiments later. But in Einstein's first paper, he calls it a light quanta, and it's in German, but it says light quanta. Number four, the simplest conception is that, this is a quote out of his photoelectric paper, the simplest conception is that the light quantum transfers its entire energy to a single electron. When greater than the work function of the metal, the electron is liberated with the observed kinetic energy. That explains the threshold frequency. If you don't have enough energy, you don't knock the electron out. And so this is what Einstein proposed, and it was a hybrid of two metaphors, particle and a wave. All right, let's continue on. So I'm going to look at threshold frequency. The threshold frequency is dependent upon the metal. If the metal is holding more tightly to the electron, then it's not going to allow it to be liberated. And so you need a higher frequency or a greater energy photon or quanta, light quanta. All right, hit enter. So this axis over here shows the electron kinetic energy. Yeah. This is a threshold frequency of one metal, threshold frequency of a second metal, threshold frequency of a third metal. And so you had different threshold frequencies for different materials. And in fact, you can identify unknown materials by knowing their work function. And something interesting else something else that's interesting here is that your slopes are Planck's constant. And every single slope for every single metal is always Planck's constant. So hit enter. Planck's constant is represented with an H. Should be H bar, but it's H here. Go ahead. When you graph several metals on the same graph, you'll find that they have different thresholds, but they always have the same slope. Because, see, the slope is indicated by something that's constant in nature. That is, the larger the frequency of the photon coming in, the greater the amount of energy it holds in that packet. Do another one. And so I have three metals here, three threshold frequencies. All right, continue. Now, nothing happens down below here. But what Einstein said is that that number has meaning. That's how deep in the electron, in the surface of the metal, that's how deep in the metal the electron is located. The deeper it is, the higher the energy of the packet that is required to liberate it. So hit another one. That's the work function phi. You'll notice that as the threshold frequency goes up, this goes down. This goes deeper. It gets harder to knock it out. do it again. And so we have here, it's quite interesting. We have slopes that are the same for all three of these tests. The HF is independent of the metal. It just describes the amount of energy that is contained in a light quanta coming into the metal. So go ahead. And so EK equals HF minus phi, Planck's constant electron ejection energy. Continue on. Okay, here was your data today. Okay, so I've entered in 35 data points. And the accepted value for Planck's constant, which is known rather precisely because, you know, the chemists started getting involved, making sure we did it right. And it's 4.135667662 times 10 to the negative 15th electron volt seconds. Now that the seconds comes from the hertz. The hertz is on the bottom, so then it comes to the top and all that. Our value for Planck's constant that we got was 4.082 times 10 to the negative 15th electron volt seconds. And by the way, that's really, really good. And in fact, we had just a negative 1.03% error. And when you consider that you all were novices using the machine, and the machines were brand new, you know, we just put them together yesterday, and you consider everything going on, 1.3% within the ideal value is actually pretty good. So you should be congratulated. Got a lot of talented budding physicists in the group here. You should feel pretty good about it. And there I have the data points. And you can see that this right here is your work function. That's how much energy it takes to get an electron out. Think of it this way. You might think about it this way. There's a hole, and how deep that hole, you put a ball in the hole like a basketball, and you got to knock that basketball out, right? Well, let's say the basketball is 30 centimeters deep in the hole, not very deep, okay? And you throw a ping pong ball at it. Does the basketball come out? Probably not. But if I shoot a cannonball at it, right? If I drop a cannonball on that basketball, it comes out of that hole. So it's a matter of how much energy coming in do you have available to knock it out of its location. All right, continue on. Robert Millikan was totally convinced that light was a wave, and he intended to disprove the thesis that Albert Einstein had proposed for a light quantum. He thought if the experiment was done carefully and in a vacuum, there would be no ejection of electrons. And for example, he thought, well, if I increase the intensity of the light and we're in a vacuum, we'll knock those electrons out no matter what as long as I make the light bright enough, no matter what the frequency is. 7 years. He had Ph.D. students and undergraduate students and all sorts of other slaves working hard, and they tried their best to disprove Einstein. And in a tribute to his integrity, he admitted that Einstein had the right metaphors on this. He didn't like it. He was convinced it was a wave, but he was convinced also by the data. It took 7 years. Einstein was nominated by Emil Warburg in 1917, and he was awarded the Nobel Prize in 1921. So he got the Nobel Prize 17 years almost, after he wrote the paper. That's a long, long time. And the reason why I think is because he was asking for a blending of two metaphors. And I don't think it's hard to find that sort of doing in science. Einstein's law of the photoelectric effect has been extremely rigorously tested by American Millikan and his pupils and passed the test brilliantly owing to these, this is the exact words from the nomination. Owing to these studies by Einstein, the quantum theory has been perfected to a high degree, and extensive literature grew up in this field whereby the extraordinary value of this theory was proved. I'm just going to talk about some of the experiments that Millikan oversaw. Guess what he had here? He had current, and there's a stopping voltage becomes negative, and as it becomes negative, the currents converge. Now, what causes current? What causes current is intensity. What's intensity mean? That's the number of particles coming in. That's the number of quanta coming into the surface. And so then the brighter the light, the more the current. Most of you know that because you saw that when you did the simulations. And then when you went negative on the stopping voltage, you would stop all that current. Because one theory was, well, if you put enough current, if you put enough light, brightness of the light in there, you should have so much current it gets harder to stop. But it doesn't. It still stops with the same stopping voltage. Different frequencies or different metals will have different cutoff voltages. It has nothing to do with how much light you're using. It has to do with the nature of the metal that you're impacting. Saturation current, here's a voltage and the current. And what happens is you reduce the voltage, you come to a stopping potential, and then it stops all the current. All right, continue on. Here's a little summary. Using Albert Einstein's quanta photon model, a good theoretical model always explains the results of multiple experiments. The neat thing about Einstein's photoelectric effect was he explained only the photoelectric experiment done by Leonard. But it ended up that that same model explained a whole bunch of other experiments. And so in this case, as we increase frequency, this is not, by the way, in your simulations, so I don't know if I should be showing you this. If you increase the frequency, the current goes up, and then finally, like, it tops out. And then, surprisingly, when you get beyond a certain frequency, it will start to drop. And I've actually done the lab and seen it. It's very confusing, but what happens is some of the higher frequency photons are going to deeper, they're going to deeper electrons and liberating electrons that are harder to liberate, so they're at second ionization level. And it actually drops your current a little bit when that happens, because the chances of it are reduced. The chances of hitting it correctly, that deeper electron, are smaller. And so the probability is reduced. But it's not something in the simulations, so it's just something that I've actually seen in the lab. All right, so here we have electron ejection energy as function of frequency. We know that one pretty good by now, don't we? You'll notice that the electron ejection energy has a threshold frequency where it just starts to work, then below that it doesn't work. Here we have intensity of the light in lux, and it goes up until finally, now in your simulations, the intensity just went up and up and up and up and up forever. But in reality, it reaches a threshold, and it won't go anymore. And let me tell you the reason for that. It is because there are only so many sites on the surface of the metal. They have like little honeycombs where if the photon enters that region, it liberates the electron, but if it hits outside or between those regions, it does not. So what happens as you reach saturation, that surface of that metal can only allow so many electrons out because it's got only so many locations where that can happen. And so that it can be used to explain why intensity does not cause ever increasing current. Unfortunately, your simulations would continue increasing infinitely, but that's not the way it is. And in fact, think about solar cells. Part of the problem is packing them close enough together so that they can produce more current per square centimeter of the device. Then here we have electron ejection energy as a function of intensity, and there's no function. Like in Algebra 1, you'd say, no function. When I was in Algebra 1, I didn't understand that. All I knew is flat lines are parallel, no function. That's what I'd write. But what that means is it doesn't have anything, the intensity has nothing to do with the amount of energy an electron has when it comes out. That is really, really hard because it's so counterintuitive. Einstein's work predicted that energy of individual ejected electrons increased linearly with the frequency of the light Perhaps surprisingly, the precise relationship had not at the time been tested. By 1905, it was known that the energy of the photon electrons increased with increasing frequency of the incident light and is independent of the intensity of the light. However, the manner of the increase was not experimentally determined until 1914, when Robert Millikan showed that Einstein's prediction was correct. So some people would say, oh, they should have shared the Nobel Prize. That's an interesting thing, isn't it? Like the guy who came up with the idea or the guy who confirmed it. You know, how should that work out? Well, it ends up that Millikan got Nobel Prize for something else a couple years later. So we'll leave that because that's a big, long thing, too. The grueling 2,600-year review is now over. And this is the birth of quantum physics, where it's both a light and a wave. It's not just one or the other.